It is our great honor and privilege to introduce Amy Ross from NASA as our closing speaker. This has been our dream to have someone from NASA from the very first time we first started thinking about what a design conference for the outdoor industry might look like. And we're really thrilled to make it a reality and to share it with all of you. So thank you and welcome, Amy.
I'm glad to be here, and thank you for having me, Sam and Michelle. I really appreciate it. So, okay, I'm going to confess up front, I am an engineer. Sorry, my slides are going to look like an engineer put them together. I had a friend who did these slides and presented them earlier, and then I messed with them some, and I definitely de-designed them a lot. So just be prepared. And I've got a lot to talk about. I can talk about spacesuits all day long. So when you just give me an hour, I have to smush it in, and then that just means I talk faster, is really all it means. Okay, because I want to give some time so you guys can ask questions, because I really want to make sure that you get your questions answered. And that's the real intent here. I am a mechanical engineer from Purdue University, and I got started at NASA by doing the cooperative education program. So that meant that after my freshman year, and a summer semester in which I got a C in statics, would you believe it? It's like, that's not discouraging to be an engineer and go to NASA. I don't know what it is, but I went ahead and started at 19 years old at NASA Johnson Space Center. And I've been working at NASA Johnson Space Center ever since then. So that means I have 25 years in and working on research and development for advanced spacesuits, which primarily means spacesuits that go to planetary surfaces. Okay, there is exactly one of me in the U.S. and as a lead, and I have a team of 4 civil servants, 3 contracting engineers, and 4 technicians. That's it. That's us. There's a community of vendors as well that we work with, but it's a small team, and so it's a fairly unique kind of a job. So I'm very happy to share it with you today. So what I'm going to talk about is why do they look like that? Because one of the comments we get, and we've talked to people, I have a friend at Nike, and they had people come down to Johnson Space Center, and we talked, and they said, well, why don't you make it look cooler? I'm like, it's a spacesuit. To me, it looks cool. But, you know, we've been Hollywoodized in our idea of what spacesuits could and should look like, and they don't look like that. And there's good reason. So we're going to talk about that today. But when I was thinking about what you guys think about as design, this is what I pulled some pictures up of. And so I thought, okay, this is probably where they're coming from. And so they do think about where they're going and what they're doing when they're designing. But they also think about how it looks. Okay? And so we're going to talk about how I don't think about that part hardly at all. So this is what my spacesuits look like, and there's a variety of them up here, and they all look a little different, and there's a reason for why each one looks a little different. We're going to talk about that. Okay, so when you are going to design a spacesuit, like probably what you design, you have to think about 2 things, and primarily 2 things. Where are you going? So what environment are you going to put yourself in? And what are you going to do? So if you're going to design something for skiing, it's going to be something very different from a water skiing kind of sport activity. And that's the same thing with us. You know, you got to decide where you're going and what you're doing. Okay, for us that equals, uh-oh, what happened? Why won't it go? There we go. Requirements, okay? That's the engineer language for those things. Specifications, another word for it. Okay, this is the office for the International Space Station astronauts. That's where we're going, okay? So it's approximately 250 miles up. And what kind of environment does that mean that we have? Well, it's a vacuum. That's kind of a special requirement. There are extreme temperatures, and I know you guys deal with extreme temperatures, but we'll talk about what that means to us. Radiation, okay, other than sunburns, probably not a big problem in your lives, but we'll talk about that. And micrometeoroids. Again, probably not something you worry about very often. But we do. So let's talk about vacuum first. Okay. I asked small school children what a vacuum means, and you know, hey, it's the thing my mom uses to suck up dirt from the floor. No, yes and no. It really means that there's an absence of air, okay? We all know humans need air. Oxygen. So you will die within minutes if you don't have oxygen. It's okay, because you'll be unconscious by then. Okay? So this is something we prevent, though. The pressure garment at its base is a life support system. Okay? It's a life support system. And this is one of the things that makes it a life support system. Our number one job is to protect you from the extreme environment, to keep you alive. Okay? And then we'll worry about what you're doing. But first of all, keep you alive. Okay? Then another thing to talk about with a vacuum is that the boiling point of water is directly related, anybody who goes high country knows this, to the temperature, the pressure that you're under. Okay, so the temperature at which water boils depends upon the pressure. The higher you get, the lower the temperature that water will boil at. Handy to know. In a vacuum, water will boil at 98.6 degrees Fahrenheit. Okay? Actually, it will boil at a lot lower temperature than that, but we all recognize 98.6 degrees Fahrenheit. We had a gentleman, when we were doing spacesuit testing back in the Gemini program, and he was on a treadmill in a vacuum chamber, and the hose became disconnected from the wall. He remembers the saliva on his tongue boiling off. Okay? So, before he went unconscious, but he's alive to tell the story, so it all turned out okay. He ended up being my deputy division chief. He's good. He's fine. Not too many brain cells lost. Now, the way we do that is we create a human-shaped balloon and then control that balloon. So these are two very important layers of a spacesuit. This, and these are exotic materials, I'm sorry. Urethane-coated nylon, polyester. Okay? The magic of a spacesuit. Urethane-coated nylon and polyester. So this is called the bladder of the spacesuit. That's the gas retention layer. And then you want to manage your balloon, okay? Using the restraint layer is what we call it. Okay? Okay, and here's my little fabric swatch, okay? And so we're talking about, out of all the layers, we're talking about these two layers here. Okay, and you can see the red arrow points to those two layers. Okay, because this, in case I didn't say, is the layup of a spacesuit. So it's this between you and death, okay? That's what we're talking about. Okay, astronauts get cranky if they think they're gonna die. It's not good. Okay, so extreme temperatures. What are the extreme temperatures we're working on with? Well, minus 150 to plus 250, okay? When I talk to my school children again, I love to bake chocolate chip cookies. 350 degrees is chocolate chip cookie baking temperature. Do you want to do your homework in an oven along with the cookies baking? No, I mean, you don't. That's uncomfortable at the very least. So, but that's what we're shoving our astronauts out the door to go do their work in. And not only that, but they're orbiting Earth in low Earth orbit. And so every 90 minutes, they go all the way around. So by the time it takes you to watch Mulan, it's going all the way around Earth, okay? Think about what you're doing with your time. And so half of that time, 45 minutes, they're in the sun, and the other half, they're in the shade. Okay, so you're going between these two temperatures every 45 minutes, okay? And then the only thing that we have to keep you from not being disagreeable under those conditions is this, okay? These are what we call layers of aluminized mylar. You know, mylar is a film material, and you just coat it with aluminum. And so we use it as our thermal insulation. There are three primary ways to move thermal heat around. This is my engineer coming out of me. Convection, conduction, and radiation, right? If you're in a vacuum, guess what? There is no convection going on because you have to have a gas, have to have a fluid as a medium. Okay, so there's conduction, right, where two things have to touch to transfer thermal energy. Well, we make sure that these are patterned so there is a little gap in between each one, so there is no touching of the layers, and so that there is no thermal short, so there is no conduction of thermal energy between the layers. And then, why are they shiny? Radiation. Okay, you just bounce that stuff back off. Okay, so basically we've created a thermos bottle around the human, isolating the human from the external thermal environment. Okay, and why are spacesuits white? Because it reflects the heat. Okay, that's why you don't make them black and look cool. Okay, so those are the layers we're talking about. And then now that we put a thermos bottle around the human, what have we created? We created yet another problem that we have to solve. Okay, so if I stick you inside of a VW Beetle and roll the windows up, what's going to happen pretty quick in there? Is it going to heat up or cool down? Heat up. Is it going to get humid or is it going to get dry? Humid. Right, because you, as a human, eat food, spit out heat and humidity, among other things, okay? Which we also have to deal with, by the way. And so then that means we don't put an air conditioner into the spacesuit because air conditioners are big, heavy, and take a lot of power. In space, we don't like things that are big, heavy, and take a lot of power. So we try to do something that's light and power efficient and small. This is it. This is a lovely liquid cooling and ventilation garment, and I'll tell you, you have to kind of suck it up the first time you get out in front of your fellow colleagues in this. This is what you wear when you get into a spacesuit, and there is no way to get into the spacesuit without them seeing you in this. So you just kind of got to get used to that. You got to respect each other when they're in this because they're vulnerable. Although that's my colleague Lindsay who authored the original pitch here, and she looks like she's got some tune with it. So I'll how you wear the socks, I think. Okay, so the water there's tubes in here. Cold water comes from your backpack, which is the other part of the life support system that I don't work on, but it's all part of the spacesuit as a whole. Cold water comes from that backpack, goes through the tubes, picks up your body heat, cools you off, and goes back out to the backpack to get cooled down again. Okay? Okay, now radiation. We really have it pretty easy, and I was going to get an image of the Van Allen radiation belts, but I was on the airplane and the Wi-Fi just didn't work that well. So we know that the Van Allen radiation belts, because of our magnetic core, kind of help keep us isolated from the really nasty radiation coming in from space, okay? So really the only space we have to worry about is some of the low energy particles. And what's most vulnerable in your body to those low energy particles are your eyes and your skin, okay? Your eyes are pretty much the only part that's really exposed because the spacesuit will protect you from the rest of it. And happily enough, the polycarbonate that we use for the helmet visor filters out that radiation, okay? So that's a good and happy thing. That's all we do. Now, if you're gonna go someplace else and you're exposed to that deep space radiation, we just collect the dosage. So we just know how much radiation you're receiving, okay? Which is that lifetime exposure. Now, micrometeoroids. Actually, I should say roid. How big is it? That's actually a really big one because it's up on that screen. Think about the tip of a pencil, the little ball in your roller ball pins. Okay, that's what we're talking about. Now, why is that scary? Anybody know? Speed, very good. Okay, because good old Newtonian engineering. So that's what a ball, you can kind of see the scale, can do to a steel plate. That steel plate, I think, was a ½ an inch thick, just for calibration. But Newton tells us that kinetic energy is equal to 1/2 mass times velocity squared. In low Earth orbit, we are traveling 17,500 miles per hour. Okay, I grew up in Indiana. Well, I'm from Indiana, and so Indianapolis 500 is an annual tradition. Those people are traveling 300 miles per hour, right? A bullet, 10,000 miles. No, what is it? 800 feet per second. Okay, nowhere near this. This is 17,500 miles per hour. 17,000. Think about that. So, and then you square it. Okay, it's a big number. Now you have to manage your kinetic energy. Okay, there's 2 ways to reduce your kinetic energy. You can reduce the mass. It's already a little bitty thing. Okay, so that's not probably where you want to deal with your energy reduction. So you got to deal with the velocity. So how do we do that? Well, it's built into the layup of the spacesuit, believe it or not, because steel plating obviously is not going to do the job. So this stuff. This is one of the things that we really, really like when we do spacesuit design. If you can get double bang for your buck. The same thing that does your thermal insulation is also, believe it or not, your micrometeoroid protection. How's that work? Well, unlike a ballistic impact, like a bullet, which is order of magnitude below the velocity of the hypervelocity impactor, what happens is, of course it's going to go through this first layer, okay? But what happens when it hits is it causes a shock wave. That shock wave shatters that impactor and starts to slow it down and break it up. So as you go through each layer, you're going to see a bigger and bigger damage pattern. It looks like you're doing a really bad job. But in reality, you are absorbing that energy and taking all the badness out of it, so that by the time it gets to what I call the backstop, it's a neoprene-coated nylon, you have taken the energy out of that particle. And we have 99.999, I think there's a fourth 9% chance of no penetration, probability of no penetration for the spacesuit in the environment we are in low Earth orbit. So we try to do a good job there. Okay, and so that's what I just said. And there's that layer again. Okay, now, we talked about where you're going and some of the problems with that. Now, what are you going to do? We ask our astronauts to do fairly challenging things like building space stations when they go outside. This guy here is probably going to go to that umbilical that's in that bundle and go move it around. Okay? I don't know if you've ever tried to manage rope, but when you try to do that in space, it really doesn't behave. It's challenging. Move masses around. So one of the things that happens on space station is things wear out. We have these boxes that are called on-orbit replacement units that are different systems in a box that you can just take the old one out and put the new one in. But it's a big mass. And then, you know, this is a truss of the space station, and those yellow things are the handrails, and so you have to translate around here. And some work sites are like inside of the bays of the space station as well. Okay? So we give them some fairly challenging things to do. What do we do as far as mobility to give them the capability to do those jobs? Well, the spacesuit for low Earth orbit that we use on the space station is a modular system. I like to think of it as the Garanimals approach. We don't have suits for everybody. We have components that we put together to mix and match for people, like when I have to buy different size top and pants when I go to the store. So this is a fiberglass, just regular old fiberglass composite hut. Fiberglass because it was built by United Technologies Corporation. They build propellers. They're real comfortable with fiberglass. I'm pretty good with it too. But then most of the soft goods are built by a vendor called ILC Dover, and they are located in Delaware. Okay, and so you can see there's a shoulder and then a lower arm, and you can see what the lower arm looks like over here when it's naked. So it doesn't have its thermal micrometeoroid garment on it. That's just the bladder restraint assembly like we talked about before. Okay, and then the glove, just so to show you, since I've got the layers here. Glove bladder, which looks different. It's not that yellow fabric because you want the glove to be more flexible. And so the unreinforced film is more flexible. That's why we use just this bladder here. It goes into a restraint assembly, okay? These are stitched, no kidding, by little ladies up in Delaware. And they are very good at their jobs. I don't know, you guys will appreciate this. Not very many audiences will. They have, especially like on the TMG, where it's multiple layers here, thermal micrometeoroid garment, there's multiple layers that they're stitching together, especially up here in the finger seams. And their tolerances are like plus a 16th or 32nd, minus 0. I mean, it's pretty fine manufacturing required, and they're good at it. Only the best ones do the gloves. Okay, and then the whole assembly looks like that when you put it all together. Okay, so that's that. Now, there's a top and a bottom, and this is the bottom, the lower torso assembly. And I do want you to notice something about this lower torso assembly. Right here, I lost my clicker. I knew I would do that. Here you go. This right here, it's hard to tell, but that's where the bearing is. That bearing on that spacesuit rides right about here. Okay? So it gives you some ability to reach around like that. Okay, and when you're cutting in space, you kind of sit back a little bit, so that kind of works for you better. Think about that if you're trying to not be in microgravity. We'll get back to that. And the boots, does this look like anything that you'd want to go backpacking in? No. That's okay, because that's not what its job is, okay? This is a microgravity suit boot, and so what it is it has a fiberglass sole here, nice flat, big clown shoe fiberglass sole, and I'll show you why it is in a minute. But yes, there's a reason it looks like this. Notice also the clip on the back here, okay, that metal component here. There's a reason for that too, and we'll tell you here in a minute. Okay? There's also, like I said, that other stuff that other people work on. There's a display and control module on the front of the suit. That's what controls the life support system, backpack, portable life support system, or PLIS, on the back of the suit. And so you have to tell your spacesuit what mode you're in. The astronaut has the ability to change the amount of water flow through their LCVG to adjust their cooling level. They also have the ability to flip through some screens and see the status of their system, and they have the power to turn on and off some of the components, as well as tell the suit what mode it is in, like if it's in the airlock or if it's outside doing EVA, those kinds of things, or checkout mode. So that's on the front of the suit. And then the PLIS is a gigantic box on the back of the suit. We have a going rivalry between the two teams, if you can't tell. So we tell them that this should be the size of a Coke can, and then we'd be happy. They don't like us. Okay, so now here's the answer to the boot question. You have to interface with different things. This is called a foot restraint. So it's really helpful when you're in microgravity. This is normally how you get around, not these things. And so when you want to do work, you need to stabilize yourself. You're floating. So what you do is you put your feet in the foot restraint. That's why it's this nice flat stable sole with a nice little clip to clip yourself into the foot restraint. That's why that's like that. Okay, so get your foot in the foot restraint, and then you can do work at your work site, okay? And to help you do your work at your work site, you have tethers to make sure things don't float away from you, okay? And you have what's called a mini workstation, so this is your tool belt for your spacesuit, so everything's handy right there in front of you. And then you also have the system has features that allow you to mount yourself in the airlock so that people can get in and out of their spacesuits while it's being stabilized or held in place, okay? Now, what's next? This is the question I like because that's what I want to talk about. This is what I work on. What's next? We hope to do this kind of thing. Well, maybe not this kind of thing, okay? But we got a bunch of Type A astronauts who are going to be bored after spending 6 months in space, so there you go. They might want to go do that kind of thing. I go, I don't care what you say, I'm going to go. So, of course, when you go someplace different, guess what? New environment, new things you're going to be doing. You probably are going to need to be more capable because you're going to need to be more on your own because the comm delay in between here and Mars is like up to 20 minutes each way. Okay, so you can ask, hey, I'm about ready to fall down, what should I do? And wait 20 minutes for that to get to Houston and another 20 minutes for it to get back. You need to be able to make some of the decisions yourself and have some capability on your system. And of course, you're going to have new tools and new vehicles that you're going to be working with. Okay, just to highlight the difference between some of the types of environments that we have to deal with. So this is atmosphere on Everest. It's 0.2 of an atmosphere. Okay, the best we can do on Mars is 0.006. Okay, it's different. These are the yeah. These you can live in this, maybe not so happily, but you can not here. Besides, the air is mostly carbon dioxide. That doesn't work so well either. And then extreme temperatures. So I've actually been to, what is the town? Shoot. I've been to the little town where they have a thermometer that's 134 feet high, because that's the highest temperature that they recorded in Death Valley. Okay, and we were doing a testing there, and so in the evenings there was so much to do there that what we did was we set up our lawn chairs in the parking lot and watched the temperature come down on the big thermometer. Not Barcelona. I'll have to remember that. And then you can see space. This is low Earth orbit, and then we kind of get some relief on the hot end on Mars, but look at the cold end here. Okay, you probably don't think much about this. I do on a routine basis because it can kill you. And then dust, same thing. It can kill you. Okay, so we have to worry about those things. Not that you don't, but they usually don't kill you. Okay, and 40 million miles from Earth is how far away space is, Mars is. So 250 miles up, 400 million miles away. Okay, 40 million. And again, just to kind of say Mars surface, here's some of the kind of characteristics. And here's some of the things that we think we might need to be doing. And, fix your car, house repairs, okay, do some science, hopefully, drive around. So we need new tools to be able to handle these new kinds of challenges in our spacesuit design. Thermal insulation is one of them, because the insulation that we have depends on the vacuum. It is effective in a vacuum because that convection isn't around. But once you hit an atmosphere, the convection starts to kill the capability of this insulation. So we are looking at something that you guys probably are aware of as well, flexible aerogels. So we've been working on that for over a decade to try to get them where they are at a place where we can incorporate them into spacesuit designs. And we've actually just incorporated, for the very first time, something that's reasonably feasible for a spacesuit application into a glove thermal micrometeoroid garment in the last year. So that's a pretty good milestone for us. It's not that we take so long to do our job, it's that we have to poke at it very slowly. I work at a flight operations center, so the focus is first, International Space Station operations. Second and third, although they argue who's who, is commercial crew program and the Orion program. And a very, very distant fourth is research and development. So I do have a budget. I'm very happy about having a budget. I have a team. I used to be me and Joe, and now there are the 5 of us. So that's very, very exciting. But it just takes a while because I have to pick at a little bit at a time. Okay, and then dust. So when you are working with oxygen systems, normally you have a clean room with your oxygen systems. Okay, we don't have that luxury when you're trying to do space operations, and we do have 100% oxygen in the spacesuit. And I don't know if you've ever seen some of the videos out of White Sands Test Facility, but you should see if they're on YouTube, because they are exciting. I used to work with a gentleman who was an expert in flammability, and his mantra was that everything burns. Inconel steel burns. You get enough pressure, enough oxygen, it burns. So you have to be very, very careful when you're dealing with oxygen systems and the cleanliness level and how you're dealing with foreign object debris. You can, like on the last picture, you can get that dust. Lunar dust is actually harder because it's broken glass basically, and so it can abrade and also abrade through your bladder, your gas retention layer, and that's a bad thing. But it will also affect your wear, your durability of your garment, as well as potentially changing the thermal aspects of it. You know, in general, we want the spacesuit to be white for thermal reasons. Well, once it gets dirty, guess what? It's not doing that same job anymore. So you got to make sure you design for that. Okay. And then perchlorates are in the soil. Okay, they're toxic to humans. So once they mix with oxygen and humidity, it forms an acid, and that acid's corrosive. And so if you get that into your lungs, it's a bad thing. And if you get it on your suit, it's a bad thing. Guess what leaks out of our suit? Oxygen and humidity. So we're gonna have to figure out how to deal with that. And then you can, in fact, we've got bearings. One of the ways that we allow a pressurized garment to move, so think you're wearing a scuba tank, okay? Not a scuba suit, scuba tank that's shaped like a human, and now you want it to rotate. How do you make that happen? Well, it's like also a big balloon animal. So if you've ever tried to make a balloon animal, you know you make that first turn, but if you let go, it goes right back to where it was. Okay, so if you're in that balloon animal trying to move it, first of all, you have to create that motion, and then you have to fight it the whole time. Or, like in the scuba tank scenario, you have to even just make that motion occur at all, and that's where bearings come in. So we have a bearing here, at the upper arm, at the wrist, at the waist, at the hip, maybe a couple, 3 of them, at the ankle. So we've got a lot of bearings in our suit to allow the mobility. So they will leak, because if you've got a seal, it's still gonna leak some. And so, and if you get dust in that seal, they're going to get leakier, and they're also going to get stickier too, especially if you get dust all the way into the race. You know, you're going to start having grinding bearing sounds, and that's unpleasant. Okay, now we're going to have to try to mitigate the dust. So one way we can do that is it's going to be a multi-pronged approach, right? You're going to need to go ahead and try to keep it off the suit as best you can, and there are a number of ways to do that. So there are coatings, there's these electronic methods, there's different ways to do that. But then you also probably need to employ some kind of a dust protocol. So you're going to need a mud porch. You're going to need to come in and have some way kind of cleaning off and keeping that contaminant from getting into your habitable area, okay? So this is a system level thing that is going to be needed as we try to design not just the spacesuit, but the entire mission hardware. Okay. Okay. So what are our tasks? Well, when you go to a planetary surface, kind of like when they went to the moon, a lot of what you're going to want to do is it shouldn't be called geology, but geology, right? Whatever you call Marsology. Geology. So you're going to take soil samples, you're going to map the terrain, you're going to map where the boundaries between different types of soil and terrain are, that kind of thing. So this is when we used to do field testing out near Flagstaff, Arizona. Near Flagstaff, Arizona is where the USGS has their planetary division. And so they have identified places that look like different parts of the lunar surface and different parts of the Martian surface. So we would go out to those places that are analogs to the planetary surfaces and do the work that we think we need to do to understand how well our spacesuits are actually performing the tasks that they're going to need to perform. And so we would get feedback from people, including geologists that we put in the suit, about how well the suit did or didn't let them do their job and try to improve from there. Which is similar to how you test a lot of your gear, right? Okay, and then the search for life. So this is a PhD scientist who was doing an instrument that would try to discern whether life was from Mars or from Earth. So you got to understand if your traces are stuff that you shot out of your suit or if it's new stuff that's actually from Mars. And that's part of what he's looking at. And then what kind of life it is. And then here's more scientific equipment set up. Okay. Okay, so we're moving away from this kind of a suit, that's the current suit that we use on the space station, to something more like this. This is my current prototype that we just got done testing in the neutral buoyancy facility. Have you guys ever heard of the neutral buoyancy facility, or laboratory, NBL? It is 6.2 million gallons of water. It is 40 feet deep. It's a big pool. And so we did tests with our new prototype in the pool to see how well it could perform microgravity EVA tasks first, okay? So some of the differences are that, yes, this one has a shoulder bearing, but this one has a shoulder bearing here. So the shoulder bearing on the EMU right now hits me about here, okay? So if it's hitting you about there, you can't get here very well. In fact, I, in general, have to kind of reach one arm around to do something one-handed and leave this arm out, and then if I need to get around the other way, do the other way. So I'm really one-handed in the suit. The reason that is, one of those reasons that shoulder bearings are so far apart, is because it's a middle entry suit, a waist entry suit. So what you have to do is you get the pants on, and then you have to get the suits on a stand, and you have to get down underneath it, and you kind of have to kind of swim up into it and corkscrew and kind of pop up and then put the suit together in the middle, okay? If you've ever tried, been in a hurry, thought I don't want to unbutton the shirt off the hanger, I'm just going to put it on, you know, that doesn't work. I tried it the other day, I was like, I know this doesn't work. And that's the way spacesuits work too, though. They do try to get into your shirt that way, so you have to make those bearings move outward so you can actually get through into the suit. So your bearings are automatically not where your shoulder moves, right? Because your shoulder movement comes all the way up in here to your neck. Those shoulder bearings are way out here, and they're actually kind of like this. They're almost more planar. They're a little bit cocked, but not very. Whereas you can see this shoulder bearing here is placed way up in here by the neck, and it's really kind of got more of an angle to it. So you can get more of this kind of motion with your shoulder bearing, okay? So that's one of the differences between the two suits. Trying to give better shoulder mobility. We've got a waist bearing, but you can see where the waist bearing is. That waist bearing is way up here, okay? So that when you walk, and it's parallel to the ground. So when you walk, it moves like a natural human being, okay? Not like this thing that does this, right? Over on this suit. And because it's way up here, you now have room for hip bearings, okay? So you've got a bearing here and a bearing here, okay? With a joint between the two. So that lets you do some more natural walking capability kinds of things. I mean, when you work with geologists, one of the first things they do is like, hey, that's a cool rock, right? So, a little rock obsessed. But you gotta give them that. So if they want to get down and get the rock, there you go. And if you want to climb up a slope, or if you want to get down the ladder out of the lander, out of the ladder, out of the lander, you know, there's things that you need to do that include more hip mobility movement, okay? And then we also do have an ankle bearing. You can't see, but there is an ankle bearing. And then these boots look much more like a good walk-in work boot than it is. Okay? So these are some of the tools you're going to use. So that's the lunar rover there. This is a mock-up that we tried to improve on it, but we also did some analog testing with. That's another concept of a rover. It's got the suit port concept where you wouldn't go inside necessarily. Our suit, you don't get into the suit this way. The way you can get these shoulder bearings to stay is that you have a big door on the back. Okay? So you swing that big door open and slide in the back of the thing. And that's what allows you to have this kind of a concept. So you would just swing the suit door open and climb out into the rover that way. Okay? And then this is another kind of creepy robot-looking rover thing. Okay, now let's talk about mobility. This is, oh, that really looks bad that way. This is a lunar EVA. So this is the Apollo suit on the moon. And I never ding the Apollo suit, but look at it. The suit did its job, right? These astronauts did their job and they came home alive. But does that look highly mobile to you? One of the reasons it looks like that is because that suit did 3 different jobs. It did crew survival, it did micro-G EVA, and it did planetary surface EVA. Just like if you want to try to create this is my, if you want to go on a trip and you're going to a red carpet event in Cannes, you're going to the Arctic Circle to go see the Northern Lights, and then you're also going to a mud run, and you get to take one outfit. How good is that going to go? Okay? Something's not going to be right somewhere at some point in time. Okay? So the Apollo suit did those 3 jobs, and it did them, but it didn't do them very gracefully. Okay? So when you go to Mars and you've spent 6 months getting there, and you are going to be there for 500 days, and you're 40 million miles away from home, you kind of need something special to help you do what you need to do. And so you get to do you get to have a unique seat for that job. And you can see we haven't been sitting on our hands. Since Apollo, we've been looking at different prototypes, different suits. And this one looks very much like the Apollo suit, actually, if you took the cover layer off. This is an iteration between this suit and this suit, okay? And then these are just all kind of taking lessons learned from these suits to go forward, okay? So I always say that there's no bad suit. You always learn something from any suit. The joint it has or the construction it has may not be appropriate for what you need next, but you learned from it, okay? And so here is a video of one of our subjects. That's a rock pot. We tried to make a rock panel so you could have a little better terrain simulation than the floor of the plane. This is a Vomit Comet aircraft, so we're at 1/3 gravity in these videos. And you can see how they were able to kind of translate through there pretty well. This subject, I'm just going to say, it always bothers me that he doesn't swing his arms. You can, he doesn't. So, I'm going to replace this video when I get back, because I'm like, there are people that swing their arms. Why did you use this one? So you can see, though, they can stop, they can start, they can go over the rocks, they can move. And I'm just going to say, hee hee, that's me. Okay, so these are some of our Mars suit prototypes, like I showed on the previous slide, really. I'm going to just name them. This is the Mark III. This is the waist entry eye suit, the rear entry eye suit, the Z1, and the Z2. Okay? So this is circa 92, circa 98, about 2002, 2003 timeframe, 2007, and then, maybe a little later than that. And then this one was last year. Okay? Okay, so we're not going to be using that guy. Just to say. And like you guys, this is how this works. You build something, you test it, and you fix it. And so that's what I've been doing and we'll keep doing for a while now. Okay? And so if you want to learn more, there's a couple of places where you can go look and take a look at my suit and learn more about our journey to Mars. So we're looking forward to it. And now I'm happy to take some questions. I saw some hands go up here. Oh, well, no.
I'm just wondering, for your last prototype that you did for 2016, why is it gray and black when you specifically said white
Yes.
previously?
That's a very good question. Because we used it as a public engagement activity. So as part of our contract, actually, for that suit, that we would have some covers designed by students, and then we would use those on this suit because it's non-functional. It's just a cover layer. It's not, doesn't actually do the job, right? So it's just, we got to make it pretty. And we also have another cover layer that's kind of more of a red, white, and blue theme. That this one has lights in it, so we can't put that in the water. We've got a red, white, and blue one that goes in the water that I like too. So yeah, that's a good question. Okay, and you had a question.
Yeah, actually, I have two questions.
Okay.
Thank you. So my first question is, what's your thoughts on the biosuit that I believe MIT is developing?
Yep.
And the other question is just curious. I believe you use Gore-Tex. I've read somewhere that Gore-Tex works with you guys. Is that correct? And where is that in the suit?
Yeah.
Yeah.
Yeah. Okay. So on the first one, if you're not familiar with the biosuit is one iteration of a space activity suit or that was developed by Dr. Paul Webb back in the 60s. And really the concept is the mechanical counterpressure suit. Okay, so you need to have pressure on your body, right? You need to have pressure on your body because your body needs the pressure to survive, and you need to have pressure differential so your lungs can work right, okay? You know, if you go high enough in an airplane, you need supplemental oxygen. That's because there's not enough oxygen in the air at that altitude, so you have to kind of make sure you've got enough concentration of oxygen so respiration in your lungs can actually occur, okay? There are two ways to provide that pressure. One is the way we've typically been doing it, which is put a bubble around the human, pressurize it, okay? And then you're in this own little miniature atmosphere. Or you can do something called mechanical counterpressure. Think Spanx all over your body. Okay? That's how it works. It squeezes you. That's where the pressure comes from. Okay? Now, it has challenges. Despite how some people talk about it, it's not ready yet for prime time. There are a number of challenges that really, like us, materials developments need to address. They need some active materials because some of the things that can happen are that when you like make a fist and you see your knuckles and there's concavities, and you know that if you put a flexible material over that, any kind of spandexy thing, it's going to bridge the gap. It's not going to follow the contour, right? So all of a sudden, you've created this area where you don't have the mechanical counterpressure. And so now you can cause swelling, as well as even worse, compartmentalization syndrome, which means that there's no circulation there, okay? And you need circulation to clear out the junk that your cells are putting out and bring in new nutrients and oxygen and things. Okay, so there's that. And then there's parts of your body that don't like to be squeezed, okay? We don't understand the physiology enough to know what kind of pressure gradient is okay and what's not that still will allow circulation, because your arm is not a cylinder, your thigh is not a cylinder, you know, no part of you is a cylinder, and that's the easiest way to make sure you've got constant, you know, pressure is to design something over a cylinder and your fabric just squeezes that cylinder. But your body isn't shaped like that. So you need to understand that physiology pretty well, and we don't yet. And then being able to don it and doff it. And then also you're always going to have a transition from the mechanical counterpressure to some pressurized components. Because you have to have pressurized area around your oral nasal area so you can breathe, right? So oxygen can get in and your lungs can work. And imagine Spanx around your chest all day. You have to fight to expand your chest to take in a breath, and then it's going to contract, right? And then you have to fight to expand it. So you have to do something kind of complicated in this area to make sure that you can breathe without undue exertion. So it's a parallel path. We are following that. NASA has funded quite a bit of the research, both on the physiology side, materials side, and just the concept side. But it's probably right now, and you know these timelines will always change, but right now they say they want to go to Mars in the 2030s. that technology is a good 25 plus years out. So it just is, it's not going to meet the timelines yet. Now, things will change. Timelines will slide. We'll keep working on it. We'll see what's the best idea when we get to when we need to do the mission. But that's that story. So now you know a lot more about mechanical counterpressure suits than you did before. There is PTFE, E-expanded PTFE in here, okay? So I don't know if we use the, the copyrighted name, but trademark name, but it is in here. This is called orthofabric. This is a material specifically developed for the spacesuit. It was a change from the Apollo suit, okay? And it's actually 3 materials in one. It's a Nomex base. Nomex is, firefighter suit. It's fire resistant. And then it's got this cross-hatching. I don't know if you can see the cross-hatching there. It's kind of a gold. That's Kevlar. We don't use it in kind of the traditional, what you might think, bulletproof vest kind of sense. It's solely a ripstop here, okay, because it's good tensile strength. And then we do have, in with the Nomex, a weave of the PTFE, because that makes it slippery. If you're slippery, it's hard to tear you. Right? So you can't grab, it's hard to tear. So that's one of the things that helps keep the suit protected. And then also, if you happen to be near a leaky rocket nozzle and gunk is coming out on you, it keeps like a good, no-stick pan. It doesn't let it soak in, so you can go out in the sun and have that stuff boil off, and you don't contaminate the inside of the space station when you go back in. Okay? So that's that. Okay, yep. And did you have a question too?
Back here.
Okay.
Back here.
Okay.
Hey, I just had a style question. I was just wondering if on the Z1, were you going for the Buzz Lightyear look? Or what the green was for?
That's an interesting story. So one day, our vendor came in and said, hey, we're working on the cover layer for the suit, and we want you to pick out a color. And we're like, a color? Because it's white, right? And they said, no, we want to do something. We want you to pick out a color. And so I said pink. Because that's my goal in life, is to have a pink spacesuit. So far, everybody goes, no. And I'm like, so not pink. We said, well, not blue and not orange, because the crew survival suit's orange, and we don't want to do that. So one of my engineers said, well, why don't we go with this kind of green color? That must have inspired them, because then they did that patterning. And yeah, they had little Buzz Lightyears on their desks, and they went, hey. And so, yeah, we got some attention for that. In fact, Time Magazine named us one of the inventions of the year, I think in 2014. And I think it's because it looks like Buzz Lightyear, honestly. So, yeah. Okay? We try to have fun with it.
Can you develop fabrics internationally, or do you have to work with USA-only companies?
Yeah, that's a tricksy one. Normally, we need U.S. vendors. Yeah, and that's really, kind of stifling. So it makes it hard because there aren't as many, especially when we're, doing R&D and you want a little bitty batch made, and it's a fun challenge. We have a materials expert in-house. I'm a mechanical engineer. I know some. I've learned, over 25 years, you learn, pick up stuff. But we do have a materials expert in the house, and she works with a lot of the vendors, and she knows some of the folks that'll do some of that, kind of R&D work with us. Yeah. Yep. Yep. U.S. product.
So is there anything in there that's more or less off the shelf? And conversely, is there anything that you've developed that's made its way to other commercial products?
I know some of the Bliss stuff has, because they've got little bitty pumps and little bitty fans and things. As far as our stuff, well, I think we've helped the flexible aerogel path, because we did a lot of work that way. We've stolen from these little knobbies here. If you have to get in your spacesuit and it's dangling outside on that suit port concept, right, you're going to need, it's just like you got to loosen up your boots to be able to slip your foot in them, and then you need to tighten them back down so you can work on them. And so that BOA device is on, like ski boots and water ski boots and rollerblading boots and those kinds of things. So we stole some things that way. And we probably have to end up customizing it from the commercial to us so that it would be durable enough and meet all our requirements and things. But yeah, so we do steel like that. Some of the comm equipment that we use in just our prototype stuff is just off the shelf. Now for flight, we have to have custom things because not many comm systems deal with a 4.3 PSI atmosphere, 100% oxygen. So those usually have to get customized. But David Clark Company has done a lot of our comm. You know of them for headsets for aircraft and things. So yeah, we work with vendors of commercial products who then can do some of the development we need.
You must have counterparts in other countries that do this type of work. Do you guys ever talk to each other?
So, yes and no. The Europeans haven't had a suit program in a long time, and they've worked with the Russians off and on too. The Russians, though, even haven't had much R&D going on that I'm aware of for planetary suits. Their budgets have been cut in their space program as well, so they've primarily been working on just their, suit for the space station, their micro-J EVA spacesuit. And then the Japanese are doing some work. I did talk with a gentleman and get a presentation, but they haven't been real receptive to a lot of interaction. And then, we aren't allowed to talk to Chinese, so. So yes and no. Back in like the 2000 timeframe, the Russians were doing some development work for planetary surface, and they did come over with a boot that they had developed, and we put their boot on our suit and walked around and did some testing on our little rock pile out back, and then also on a treadmill. And then we put our boot on and did the same test and kind of let them see that too. And so we kind of did a little exchange there, and that was fun. It was fun because there aren't very many of us, and so getting to talk to somebody else that does what you do, kind of fun. So yeah, I did enjoy it, but there just isn't much out there.
So I was really curious, are you using any phase change material in any of the recent suits?
No, we aren't. Although there is, I know of a new concept that is talking about that, and I need to go learn a little bit more about that. We've looked at it before, and in general, the way we were trying to apply it wasn't giving us enough cooling over the duration before you needed to kind of do some kind of regen on it, and it's a little bit heavy and a little bit bulky when you start trying to put it in places, and so we haven't found a good use for that yet, but we have tried.
Cool. Okay, thank you.
Are the suits gender specific or they're unisex?
Yeah. So right now, our suit that we use on space station, where's that little guy? Oh, there he is. This guy is not. We have talked about that, and we've talked about what you would do or not do. They have, in the crew survivor world, they have made some custom suits that have been smaller and wider hipped. So that was a female size. Not very many of the men needed that. Other than that, we haven't done a lot of gender variation for the suits. We do talk about it some. More our trouble is just trying to do the size range that we have to deal with. Because, I can fit in that suit. That suit's actually a small suit, and I can actually fit in that suit and do work. But let me see. Oh. Let me get to that other picture. Oh, there we are. This suit, I can fit in. It's built for a 95th percentile male. So we have a big barrel-chested geologist that's over 6 feet tall. He wears that suit. I can get in it. I actually can do stuff in it. But does it fit me? And so we have a lot of discussions about how to write requirements for, define, fit. And we think there's a triangle. There's fit, comfort, and performance, okay? So just because you can get in the suit, fit, doesn't necessarily mean you can perform in it, right? Or on the other side, maybe you're so big that you can squeeze yourself in the suit so you fit, but it's uncomfortable and you're going to cause yourself some injury somehow, okay? So they're all connected, and we haven't, believe it or not, after 50 years of spacesuit work, we don't have any kind of good, quantifiable, repeatable way of testing spacesuits to say, like when you get a new suit in and want to check it out, so does the vendor meet the requirements, to say, check, it fits, or check, it performs, right? And that drives some people crazy. I think that's one of the reasons I'm still in my job, is because it doesn't bother me, because I can just see it and know. But then trying to take that and to decision makers and just say, trust me, I know it does or doesn't fit, doesn't work very well. So that's why the continual search for some kind of quantifiable means of defining these things that the vendor can work to, you can use in a contract, you can talk to with decision makers and that kind of thing, it is a struggle. It's interesting. It's just like when you take gear out to the field and people use it and they can tell you it did or didn't satisfy, it did or didn't work, but what's the nuance there? What's the, the intangibles usually that made it so? And that's where you deal a lot of the time, and you don't have a number from a test to put on it, right? You might have a questionnaire and get some numbers that way, but it's tough. It's tough. Okay.
Can you speak to maybe some of the other things beyond the external and the the liquid cooling for comfort, for some of them? How shall I put it? The realities of a person being inside the suit. So I'm thinking like the Valsalva device, I think it is, but I'm sure there's a whole bunch of other ones.
Yeah. So like I said, this is basically a spacesuit is a small spacecraft. We are required to do basically everything a spacecraft manages for a human, including waste management. So we go low tech on this. It ain't broke, don't fix it. Okay? So here you go. This is an old one. We have pull-ups now because they're easier. So this is not what you think it is. This is a maximum absorbency garment. Okay? Because it's a lot easier to look a crew member in the face and go, do you have your mag on? Than do you have your diaper on? But you can hear them kind of crunching around, so you know it's there anyway. And they got the big droopy drawers, and yeah. It's funny because, they're astronauts, right? Yeah, you're cool. You're wearing a diaper. Okay, and this, our Camelback friends will recognize, is basically a customized Camelback for a spacesuit. And this does not go on the back. This actually goes in the front because you want your straw where you can get at it. And so you smack this thing right in the front of the spacesuit on that hot upper torso, and then that straw is right there where you can get at it. Okay? So that's what we call the big gulp. So that's how you hydrate. We used to have a food stick in the suit, and it was fairly low tech too. Fruit roll-ups. Remember those things? It was a fruit roll-up, layered on a fruit roll-up, layered on a fruit roll-up, and you roll that puppy up, and you stick it in a little sleeve, and there you go. If you've ever had children chew on a fruit roll-up and then leave it somewhere, you know what that mess is like. Okay? It's sticky, it's nasty, it smells bad. Well, the crew members decided that they did not need that in their spacesuit. And so we don't have any food in the spacesuit anymore. That is always something we do have to kind of think about. And if you're in a crew survival suit and you maybe get trapped in that suit for, if you're going out past the moon like we will in Orion, and you might get past the point of no return, and then you have a cabin pressurization problem and you're in your suit for 5 days, you have a food port, right? You have to have some way to get something in there. And so, and then, what was the other thing I was going to do? Oh, the Valsalva, yeah. As you change pressures, like you are depressing the airlock and you're or repressing the airlock, and you're in your suit and the suit pressure is changing too. It's just like flying an airplane or going scuba diving. Your ears can have trouble, and a lot of people have to like pinch their nose and blow to make that pop. There's a little device called a Valsalva, and basically it's a little block of foam, and there's 2 versions of it. One, it's a rectangle with a little slot out in the middle, and you just shove your nose in between there and blow. Another one, we lovingly call the Dolly Parton, and it's where you stick your nostrils up in to the 2 little protrusions and blow. So, yep, that's the Valsalva. Well, I've had people come to my team and say, I never thought that I would have to learn to not be so modest at work, because you wear things like that in front of colleagues. And then I never thought I would talk about crotches so much in my entire life. Finger crotches, crotches. You work with the human body. You have these conversations.
I was going to ask, as designers, we like to test out some of the environments and conditions that our designs are for different people. So I was wondering what you've been through or any experiences to try to experience what these astronauts are going to be going through.
Yeah, I did not know that when you sign up for this job, you sign up to be a test dummy as well. And just like you don't know your gear until you use your gear, right? You can't experience what the designer is telling you unless you've also tried some of these things. So you got to go use that tent. You got to go put on that jacket. You got to go do those things. And it's the same thing for us. You're a spacesuit designer. You have to get in a spacesuit because it is a completely different sensory experience. One of the ways we describe it to some of our subjects coming in is, and one of our protocols is that we only have one person talking to the person in the suit, because their capacity to take in information is so limited because they're so overwhelmed by the other sensory experience that they are going through. It's T-Rex brain. You've got T-Rex brain, use slow, small words, right? Because you are basically putting on this exoskeleton. So I've been in over 10 different styles of spacesuits. Some of those were on the reduced gravity aircraft, the Vomit Comet. Some of those were in the water tanks, the Neutral Buoyancy Lab. I've not been in a vacuum chamber in a spacesuit, but some people have. I've been in thermal chambers in spacesuits. So you sit there and you watch a movie and they change the temperature. You tell them how you're feeling, and they have a little pill you swallow that's measures your temperature and your core, and yep. So you become a test dummy, and yes, I've done these things in a lot of different environments. We've gone out to the field. You saw some of the pictures where we've gone out to the field and we test the spacesuits. In the desert, we'd be out there for 2 weeks. We do 1 or 2 tests a day and see how we were performing as far as in a task scenario as well as just the mobility of the suit. So yeah, yep. We try to do it. And then there's the component level and just the technology level that you test as well. So, okay. Other questions?
What about base layers? Like, what are you wearing for socks, leggings, t-shirt? What are you wearing under?
We do have TCUs, thermal comfort undergarments. So to tell the truth, I'm going to go back to Lindsay. Tell the truth, you shouldn't. You shouldn't wear a base layer. To get the maximum capability out of your LCVG, you should have skin contact with those tubes, okay? Because that's the best thermal transfer you're going to get. Do I have it there? Oh, there she is. But you can see Lindsay has a TCU on, thermal comfort undergarments. One of the reasons that Lindsay always makes sure she wears those now is because one of the first times she came out in that in front of colleagues, she had hot orange underwear on. And we all knew it. So that was fun. So she wears that now. And it does just help also keep some of these little tubes from kind of making indentations in your skin quite so readily and so deep. Those are just custom, just off-the-shelf products. I don't know what we're buying now. I don't know if it's Under Armour or just, I don't know. I think Under Armour's too expensive for us. I think we went with something less expensive. But it's just what you can get kind of base layer wise on the market. And then the socks, we have a variety of socks. Some of them are just big tube cotton athletic socks. Some of them are real thick wool socks. We get the thickness really to help take up some of the extra space in the boot if your foot's a little too small for the boot. So does that answer your question? It's nothing real fancy, tell you the truth. So that is something that we're thinking about, though. Do we need to design this so you don't need those kind of garments? Is there some way you can incorporate the two together better? So that's one of the directions we're trying to head.
When we first talked with you on the phone, we were talking about how, it's not about making it pretty, how much, because, even though they're not black, we like them white, right? The spacesuits look cool. How much of the finished external spacesuit, how much of that is all just completely functional, and how much of it is some sort of finish to just kind of finish it off? That 5% finish of, is it all just completely functional? It just happens to be all these colors specifically for need?
Yeah, I'm trying to get, which picture do I want? That one. So a lot of the time, the meat of the suit is underneath the cover layer, okay? So like probably 80% of our effort goes here, right? The cover layers, not the cover layer, but the thermal micrometeoroid protection, right? The environmental protection of the suit is probably about 20% of our time. Moving up a little bit because we're needing some new material development. It is 100% functional. There is absolutely no form. The form is what it is because it has to do its job. The function defines what kind of overlap you need to have over your bearings. Like this is not functional either. Okay, this is just because it's a prototype. But you actually need to think about what overlap you have to make sure that your bearings don't get exposed to the thermal extremes, right? Because if you get your bearings exposed to the thermal extremes, that thermal energy is going to go right through into the human, okay? So you can't do that. The shape of it is all about the function to allow the mobility joint to do its mobility. So it's all function, yeah. Yeah, that's why it's so much fun when we get to play a little bit. Otherwise, we never, ever get to think about how we're making it look. Yeah. Yeah.
What role, if any, does Struktur Event construction and bonding play?
Oh, yeah, we use a variety of different techniques in the construction of the suit. So for places like where we're putting a flange on a bladder, here, this flange is how we connect the soft goods to the hard goods, like the metal components, like a disconnect or a bearing, okay? So there's usually it's either an RF weld or it's a heat seal, okay, depending on what's gonna work best in the area. We do use some adhesives, but it's usually like an over tape or something. Usually our construction is one of the welding or heat seal kind of techniques for the bladder. For the restraint, it's straight up sewing in general, okay? We do use some, like edge lock on our seams in the glove. So just some adhesives, your 1087. In some places. So, does that answer your question? No? Yeah, okay. Yep. And we've got some specialized tooling and that kind of thing. So. The expected lifespans for a suit. So the suit that we have on Space Station right now, the soft goods have, I think, an 8-year life. The hard goods have like a 20 to 40-year life. Metal just doesn't have problems most of the time if you take care of it right. And then the suit is certified for 25 EVAs, okay? So you're always trying to fight either shelf life or cycle life. And so usually what happens is you find something that you decide the suit shouldn't be used anymore on orbit, and then it gets taken down to use for training, and then once it's completely beaten up in training, then it comes to here. So some of these things probably flew in space. Because that's where they come from. We don't just build stuff to bring it out here. This is stuff that had done its job and now it's here. So, and that's one of the things we're trying to think about for a Mars mission. Do you want to build a tank of a suit that's just going to do the whole mission for you? Because we're talking about 500 days on the surface, probably an EVA every other day potentially. That's a lot of EVA. And so, do you design for that in one system? Do you try to think about how you're going to do sparing? What's the approach for that? And we don't really have a plan for that yet. One of the things that I want to do with the Z1, this guy, is I probably want to break him. I want to do a cycle life test and just see how far we can take him, see what we can get. You know, with the EMU, it's all about the money, and how long you certified it for was how long the program thought it was worth spending the money to certify it for, right? It's got margin, right? So I'd like to see where we can get. And then I know how big my job is, because I know how many cycles I need. I need like a million walking cycles. I need about 100,000 arm cycles. You know, I know these things, but I don't know how close or far away I am from being able to do that right now. So I know I at least got EMU life, but that's in like the tens of thousands of cycles, not hundreds of thousands of cycles. How many suits do I have to build? I don't know that yet. So like, it depends on the mission. Probably for a Mars mission, though, it's going to be a small enough number of people over a long enough period of time. I might go back more custom. And of course, custom's a spectrum. So I'm not going to make different size wrist disconnects and neck rings for the helmet for everybody. I'm probably going to make some things common across and then decide what needs to be more customized between. I think that's probably going to be where the trade makes sense. Because trying to do a modular system that meets the full sizing range just isn't going to be what you need. Because you're not going to build a fleet of these things, right? You're going to be building 12 at a time, maybe. You know, a flight, a backup, and, you know, a training suit or something for each crew member that's going to fly. So, yep. Okay.
Thank you so much. It's been amazing.
Thank you.
So much. Thank you.